Today we're gonna continue to talk about backprop algorithm. Okay. I think we have finished the how we get the formula for backprop using this simple two-layer neural network as an example, right? So actually, we in example that we use, there are actually two variants. So in this network, we have two units, two output units in the output layer. I think in the previous example, yes, here exactly. Next stage, we have one example. So the reason why I have these two different architecture is that I found that this one unit output is not the most general case, right? So this in this one outputs network, if we look at the weight matrix W2, okay, it's basically a we can also call it a matrix, but it has only one row that has 4 columns, so it's not that different from a vector, right? So in order to show the equation for the DWs and the DZs is correct, especially for DWs, right? The DWs is here. We basically will extend this example to a more general case on the next slide that uses the 2 units as the output layer. Okay, so here, yeah. All right, so we, so this, how we come up with the solutions for those DWs and DAs and DZs requires some time to digest. I would admit that. Okay, but also these general principles, they are easier to memorize and to understand if you consider the dimensions relationship between these two components that are being multiplied together. Okay, so this equation on the right is essentially the multiplication between two vectors. Okay, and also you can think of it a vector also as something like similar to a matrix. Okay, but the DZ here is a long thin column vector, while a L minus 1. Okay, so this L minus 1 means that it's from the previous layer, because we have this transpose operation on the A. So the transpose basically convert a column vector into a row vector, right? So the results of a dot product between a column vector on the left and a row vector on the right. So this is a little bit different from another dot product case that we might be more familiar with, which is the row vector on the left and the column vector on the right, right? So if it is this case, okay, if it is case 2 here, we are when we compute the dot product between two vectors, then we must have that the size of these two vectors, v1 and v2, should match, right? So there should be the equal number of elements in v1, v2. But in this first case here, in this first case, this dot product is not actually the conventional dot product that we are more used to here. So this case is more like the outer product. It's not an inner product. Okay, so basically you take the first elements here and multiply with the first elements here, and you put it into the upper left corner as the product here. Okay, so the resulting matrix of this outer product would be the same, will have the same number of rows as this column vector and same number of columns as this row vector here. Yeah. So another way of thinking of this process is to expand from two vectors to a matrix, and this matrix, let's call it dW, right? It is the same dimension as the weight matrix W. Okay, so on the next slide, where we ended from our last lecture, we have a general principle summarized in one slide. Should be next one. Yeah. So whenever we consider the general principles in backprop, we are actually zooming to the weight matrix that connect two layers. Okay, so just imagine that we are focusing on the weight matrix or weight and bias that connects this layer, which we called an L, and the second layer, which we called L plus 1. So there could be more layers afterwards and before, okay? And we don't actually care too much about that. We just want to know how we memorize or how we understand the formulas between these two arbitrary layers. Okay, we need to use the DZs from the future layer, okay, or let's say later layers, which is L plus 1. Okay, so these DZs are passed from the future layers, from the output layers. Okay, we don't care about how these quantities are computed. We just immediately use them. Okay, we just use these DZs to compute the DW, DV, and the DAs for our current two layers. Okay, so first of all, DW, it is the DZ from the future layer times the activation from the previous layer transposed. Okay, right. So if you look at the dimensions, so when you don't remember whether you should put DZ to the left or AL transpose to the left, then you just need to check the dimensions. Okay, because the DZ is the gradient for the later layer, so the dimension matches the dimension of Z L plus 1. So it should be NL plus 1 by 1. And AL is from the previous layer. So it's, and when we transpose it, it becomes a row vector, which has NL columns. Okay. And the results of this matrix production is to eliminating the ones, the common items here, right? And the results will be exactly NL plus 1 by NL, which is a correct dimension. Remember, right? When we define the network, we define the weight matrix for L plus 1 layer as NL plus 1 by NL. Okay, so the dimensions of the gradients matches the dimension of the weight matrix, and this is a requirement that we must satisfy. Yeah. So if you put, for example, if you put AL transpose on the left and DZL plus 1 on the right, and you transpose them, then the result would be NL by NL plus 1, which is not the correct dimension. Okay. So just the take-home message is to check the dimensions when you are confused about the computation. Okay, and next, the dB, I would say the dB is easy to remember. It's just we just copy the values for DZ, right? The DZs are from the future layers, and then we just copy it as the gradients for DB, right? So this is very straightforward. And for DA, okay, so for DA, there's we basically use the same principle to memorize it, okay? So we need to transpose, this time we transpose the W, okay? And times, multiply with the gradients of DZ from the future layer. And the same principle of checking the dimensions can be applied, right? Now you transpose the W, so the W transpose would be NL by NL plus 1, which eliminates with the dimensions of the ZL plus 1. And the result would be NL by 1, which is exactly the dimensions of AL, right? Okay, so if you switch the positions, switch the orders of the ZL and the WL, the result would be incorrect. Okay. Yeah, so I think these two equations regarding the dW and the dAs are the two most technical ones that require some thinking, but also, as I said, it's quite easy to double check, quite easy to memorize. Okay, so let's say focus on the last gradients, which is DZ of the previous layer. So note that here the layer is L, not L plus 1, right? So we actually go step backward one more. So it's basically the AL times the derivatives of the activation functions with ZL as the inputs. So this time is this multiplication is a element-wise multiplication, right? Which means we would actually, it's not a matrix multiplication, so it is not that complicated. We don't need to consider dimensions in this case. So we can just copy the DAL, which we just computed, times the derivatives of the activation functions. Okay, so I found that it would be really helpful for you to understand how those gradients connect to each other if we go through some programming practices with the help of PyTorch or other frameworks. So the advantage of using PyTorch is that I think we have already witnessed that in the previous lecture. The gradients will be automatically computed for you. So although we want to know what happens, although we should know that what happens when a backprop occurs are those matrix multiplications. But in actual usage, when we use PyTorch, we don't need to manually compute this matrix multiplication, because the framework handles that for us. The underlying implementations of computational graphs in PyTorch will automatically compute all the gradients for the variables with correct dimensions used, with correct alignments used. But we can manually check if if the PyTorch does the correct computation in order to verify that we indeed understand the backprop. So in the next few slides, I'm going to go through some practices that's in a similar way that we did for the simple computational graph. Okay. Alrighty. So, all right. So we would still use the torch.nn as our primary usage and import the packages. And this time, it'll be a little bit complex than the previous PyTorch example because we now study the two-layer neural network. Okay, remember that we use the NN linear, okay, to define the linear parts of a neuron, okay, of a network, okay, and the linear layer is usually followed by an activation layer, and in this case we use an relu as our as the activation for the first layer, okay. So after the first layer, we connect with a second linear layer. Okay, so now, because the output for the first layer is 4, right? Then we need to use the same value as the inputs for the layer 2. Okay, so these match relationship will be verified at the runtime, but not at the time that we define those modules. Because when we define those modules, these are arbitrary Python code that we write. We can use whatever number here. We can use 5, 6, okay? Because we don't call them yet, okay? We don't run them yet. The network will not know our intention, right? So, but again, it's just a reminder that we need to consider the match relationships between these layers ourselves, okay? And in this example, we set the output size to be 2, which means there are 2 neurons as the outputs. And we use a different activation function, which is a sigmoid, okay? All right, and after those model, this part, let's call it a model, is defined. The next step is to, well, we would like to initialize all the weight parameters so that just for the purpose that they are easier to read. Otherwise, after we have executed this line of codes, the weights will be just random numbers, okay? So we will initialize the weight for layer 1, right, to be a matrix like this, okay? It will be a 4×3 matrix, okay? So the input would be of size 3 and the output would be 4, okay? And the bias, we make them all zeros, okay? All right, that's for layer 1. We'll deal with layer 2 later. So we will first focus on the backward and the forward and backward on layer 1. So after the initialization, we just prepare some data, right? Because the model is ready. The pipeline is there. We're just feeding the water, right? Feeding the data. So it's a very simple toy data set, okay? It's just a 1×3 vector, okay? So, and in this particular case, we did something special, which is to require gradients for these inputs, for this input data. And this actually doesn't happen. This rarely happens in actual usage. Because we don't need to optimize with respect to data. Data is fixed, right? But here I just want to showcase that if we want, right, we can still do the back probe all the way back to the data points, okay? All right, so these 2 lines of codes are the forward pass of the network, okay? We feed in the data to linear 1, and we get something that's called Z1, right? That's the linear part, that's a Z. And then we feed Z1 to the first activation function, and then we get the activations for the layer 1, which is A1, okay? And if we look at the shape of the A1, it'll be 1×4, right? That's expected because our linear is defined to map a 3-dimensional vector to a 4-dimensional vector. Okay, so yeah, so it's, the forward pass is very easy and straightforward. Okay, And the actual computation, the underlying computation is indicated by this matrix multiplication. Here's the weight matrix, right? And the X, the input is here. So, and the computation, if we take the first row, conduct the dot product with the X, it'll be 1 times 1 plus 2 times 2 plus 3 times 3, right? Which is 14 here, right? 14, actually here, 14 here. And plus the 0, okay? So we can see that the Z1 is 14, 32, 50, 68, and the A1 is also 14, right? So the reason, right, is that the activation function, remember, the activation function is ReLU, right? So when the input to the ReLU is a positive number, we basically don't make any change to the output. It's the same value, right? Only when the input to a ReLU is a negative number, then the ReLU would cut off and only output zeros. Okay. Okay, so due to our positive inputs, then the Z1 and A1, they have equal values. All right, so the forward is quite simple, right? And in a backward, now we'll use the same trick that we used before. We would create some pseudo gradients and then let it back propagate through the network. Okay, so the gradients we create is for A1. Okay, and we let the gradients to be a vector like all ones times 0.5, which means it's 1.05 for all the elements. So it'll be basically 0.5, 0.5, 0.5, and 0.5, right? Because A1 is a 4-dimensional vector. Okay, actually A1 has 4 elements in it. Okay, all right. And after the gradients are defined, we will call backwards and feeding the gradients to the backward function. Okay, so after the backward is called, all the variables in the graph will be computed with their gradients, okay, including the X, okay, because we deliberately let the required gradient to be true for X, okay, so all the tensors, all the variables in the graph will be given these grad attributes, okay. So now it'll be, if we look at the gradients for the weight and bias, okay, so it'll be like this. So the shape, right, it remains for the weight particularly, it's still a 4/3, right, just a correct shape. And for the B, it will be all 0.5s. Okay, so it's basically copy the gradients here to here. Okay, and so in this case, the gradients from DA1 to DZ1, I think it's a special because the activation is a ReLU function, and the ReLU output shape is like this. So when the Z is greater than 1, the function is actually a linear function. So if you take the derivative of it, the derivative would be just 1, right? So when 1 times the gradients of A, it'll be basically the same value. Okay, that's why we have DZs have the same values as DAs, DA1, which is 0.5. Okay, so remember we will not now just manually check if the computation is correct, because the W, the parameter, is initialized to 1 to 12, right? So just follow the principle, the general principles of backprop, we would get something like when we compute the dx, right? Then it will be W transposed times dz, okay? And we transpose W, it will be the matrix transpose like this. All the rows become the columns, okay? And if we, for example, take the first row, compute dot product or inner product with this long vector, it will be 0.5 times 1 plus 0.5 times 4 and so on. It will be 11 eventually, right? So yeah, so which means the computation is correct, right? Which verifies our formula, general formula, right? And if we look at the gradients for dw, which I didn't show here, because it's a row, it's a column vector multiplied with a row vector, right? So basically you can times 1 with 0.5, which is 0.5, which is exactly, let me use a different color, which is exactly this 0.5, right? And if you times 2 with this 0.5, it will be 1, right? And 3 times 5 would be 1.5. Yeah, so, and all the rows, they have the same values. All right, oops. Okay, so that's pretty much for the first layer, okay? And then we'll go deeper now. Let's look at the second layer, okay? So we will do a little bit special initialization, okay? Because the second layer, it's not, it's more or less the same as the first one, but the only difference is that it has a different activation function, right? So we have sigmoid, and when we mentioned the difference between a ReLU, okay, with a ReLU and a sigmoid, is that the sigmoid will have a limit, upper limit, which is 1 in its outputs, okay? So the outputs will never go beyond 1 and 0, okay? So it actually saturates really fast, which means when the z's, when the input to a sigmoid is a little bit big values, right? Like 10 or 20 maybe, then the outputs is already really close to 1, okay? And the outcome is that when the function is really flat here, then the gradients would be 0, right? When the gradients be 0, then it'll be hard to track all the gradients back prompt, okay? Because when the gradients is 0, then everything becomes a 0. So, so when we initialize the weights of the second linear layer, when we initialize the weight matrix of linear 2, we make them all zeros, okay? So because a matrix is 0 now, and the outputs would also be 0, right? When you multiply a 0, all 0 matrix with any input vector, all the outputs units would be 0. So and we use 0 to the inputs of as the inputs of a sigmoid function, then the gradients would be a reasonable value. It would be not close to 0, okay? Because there's a slope near the middle range, near the mid-range of the mid region of this sigmoid function, okay? So that's basically why we use different initialization here. Okay. And the forward pass, so this time we use the same x, and we don't require gradients for x now. So we run the complete forward pass, which means we compute z1 and a1, right? And we let a1 to be the input for linear 2, right? And Z2 to be the outputs, to be the inputs of activation 2. So if we look at the outputs, and as expected, because all the parameters are initialized to 0 for layer 2, then the Z2 would be 0. The output would be 0, okay? And since Z2 is 0, then the output of A2 would be 0.5, okay? Which is exactly the midpoint of a sigmoid function, right? The middle of the sigmoid function is 0.5, okay? All right, that is the forward pass. Right. So here it explains why this is the case, why the output is 0.5. Okay. So let's call the backward pass. Okay. And so because this time we want to examine the gradients for the intermediate variables, which are those A1 and Z2 in the middle. Okay, not the directly, not the inputs. Okay, so we need to call these special retained gradients, because if we don't call these retained gradients for the intermediate variables, basically PyTorch will not conserve these values, will not save these values for us. Okay, we need to immediately explicitly call these retained gradients. All right, so and then we provide some external gradients to A2, right? And which is also 0.5, okay? And we start the backward, this time from A2, not from A1, okay? From the very ending position, okay? So the output is like this. So if we look at if we print out the gradients for the weights, the bias, the Z2, and the A1, okay? So it'll be basically output something like this, okay? So first of all, if we compare DB2 and DZ2, they have the same values, right? They are exactly the same. So this is actually correct according to our formulas, general formulas of backprop, because the general principle says that when we want to know dB, we just directly copy dz, right? That's correct. And then for the A1, right, we actually observe that the A1, right, remember A1 is the outputs from the previous layer, okay? So A1 is here, and Z1 is here, and if we put it in a neuron, then Z2 is here, and A2 is here, and it's W2 that's connecting them, right? So the A1 is all 0, okay? That is also straightforward, because we initialized all the weights of W2 to be all zeros. So according to the formula, the backprop formula, when we compute the A1, we need to use the DZ2, or we need to use the W transpose times DZ2. But since W are all zeros, then it doesn't matter what DZ2 contain, right? It will output all zeros to us. Okay. Right, so that's for the A1. And then, because there's another critical item we want to know, right, which is DZ2 and also DW, okay? We'll talk about that, DW2. So now let's look at why DZ2 has such a value, which is 0.125, right? Because we have the DA2 is 0.5, right? Let's see why we have, how we come up with this 0.125 values, okay? So it has something to do with the activation functions, okay? So let's recall the gradients, the derivatives of a sigmoid function, right? We remember this formula, right? So when we talk about the sigmoid function, which is sigmoid z equals something like e plus negative z 1 over this, right? So when we take the derivative of z, it will eventually give us something like a times 1 minus a, right? And a is just this one, okay? So we will just use the activations to compute the gradients for dz, okay? So we just use this formula to compute the gradients for dz, given the gradients of dA, okay? And we copy the values from those tensor and store them into a new variable with np as with appending variable names. And this is the dz2 that we compute manually, right? Which is a2 times 1 minus a2 times the dA2, right? These external gradients is something is the gradients we directly feed to dA, okay? And then we also copy the dz2 that PyTorch automatically computed for us, right? That's the gradients attribute for z2. So, and we examine whether they have equal values, and without accidents, right? We basically can compute it correctly. Okay, so the computation that we put in this formula is 0.5 times 0.5 times 0.5, because this 0.5 is the manual gradients that we directly provide, right? So we will have 0.125. Okay, so as expected, the output should be all true because they equal, and the dz2 would be this value. All right, so that's how we compute dz2. So this has something to do with the activation functions. And what if it is the what if we use a different activation function? It should definitely influence the values for dz2. For example, ReLU, right? And maybe for ReLU, it'll be a special case because the input for this layer is 0. And when we have at the 0 point of a ReLU, technically it is the derivative is not defined. Yeah, but I don't know how PyTorch handles that. Yeah, if you are interested, you can try it yourself. Okay, that is the dz2. And lastly, we just manually check dw2. Okay, use another equation. So for dw2, we need to use the activation from the previous layer, which is A1, right? And we copied it from numpy, okay? And we will use the multiplication between dz2 and the A1. So this part is a little bit inconsistent with the general principle, because the general principle says that we need to use dz2, right? The formula that we wrote mathematically is dz2 times A transpose, right? That is what we want. But since numpy handles the dimensions a little different than our abstract mathematical thinking, because in numpy, the dimensions is basically like 1, 4 or 1, 3. Okay, and the data that we feed to the network is also 1, 3. Okay, so the data itself is not a pure 3 elements vector. It has an additional 1 dimension here. So it doesn't really matter we transpose which dimension, but the thing is that we want to make the dimension match, okay? And we want the output dw2 to have the same dimension as w2. That is the principle that we need to follow, okay? So now we put the dz2 on the left here, and the old values for A1 to the left. Okay, and this is the so-called outer product that we need to conduct, right? We basically like use 14 times this 0.125 and use it as the first elements, the upper left elements, and 32 times this one as the second elements. So the result would be a 2x4 matrix. So this is not aligned, but the result will be basically, would be a 2x4 matrix, which is the same shape as DW2 as W2. Okay, so the 1.75 is the results of 14 times this 0.125, and this 32 times 0.5 would be 4, would be here. The 6.25 would be here, and the 8.5 would be here. Yeah. So yeah, how this is the how DW are computed. All right. So until this slide is done, we are pretty much have gone through the forward and backward process in a so-called neural network model. All right. So luckily, we don't need to carry out this computation ourselves manually, because as you see, PyTorch handles that pretty neatly. I see a question. So
yeah, Professor, I have a question.
Mhm.
On this calculation, when you multiply 14 with 0.125, then second 32 should be multiplied with the bottom one. I got confused over there. The multiplication thing, like we do matrix multiplication.
Oh, you mean the multiplication is not correct?
No, it should be correct. I mean, I couldn't able to understand it. So when you're multiplying 14 with the 0.125, and
Yeah,
then you 32 multiply with the upper 0.125. I thought
yeah,
we need to multiply with the lower one.
yeah. The lower one also needs to be multiplied. So the multiplication between 14 and the upper 0.125 would be the results of the first row and the first column.
Or maybe the basic question which need to ask, matrix multiplication, this is not looks like a compatible uh, multiplication. It's 2 into 1 into 1 into 4, which are not compatible matrices.
Yeah, so the matrix multiplication requires that the element, the matrix on the left, which is a 2x1, should has a match dimension with this 1x4, right? So as long as these two quantities are equal, then it is a valid matrix multiplication. So the number of columns, yeah, the number of columns of the left matrix is the number of rows of the.
Sorry,
Yeah.
my bad on that one. But now when we are multiplying it, oh, you just showed a first example of multiplication, not all the 4 members.
No, I didn't show all the, yeah.
Oh, yeah, I thought, okay, sorry. Yeah, you were right. I mean, I was got confused a little bit.
Yeah, I didn't show the results complete process. Yeah.
Thank you.
Yeah, it'll be great to make this clarification. Yeah. So anyway, the results would be a 2x4 elements for this particular example.
Yeah.
All right. So yeah, I think it will be really helpful to go through these practices by yourself. So it lets you understand what's really going on within PyTorch after you call the backward function. Like it's actually a lot of computation going on, and all the gradients are correctly computed for you. So you don't need to like manually check the dimensions and compute all the matrix multiplications. All right. So that's a complete running through using PyTorch as an example for backprop. So next, a little bit intuitive interpretation on backprop. Okay, so the algorithm or the backprop process indicated by the backward arrows in the network color in this red color, it's basically indicates a process that we use the information from the output to updates all the parameters, updates all the nodes in the graph that help contribute to the output. Okay, so in this first example in the upper half of this slide, when we compute the output for DZ1, okay, for this particular unit, actually the 4 activation units here, all those 4 units in the previous layer, they all contribute to DZ1, right? If you look at the formula, right, when we compute the Z1, we actually uses A1, A2, A3, and A4, yes, okay. And so when we want to compute the gradients of all the parameters here, W11, W12, 13, and 14, we need to consider the A1, A2, A3, and A4 because they multiply together, right? So we need to basically use the gradients for Z1 and multiply those coefficients A1 to A4. Okay, so that is where the formula for dW2 is from. So why we need to transpose A1 and times that with and compute the multiplication between DZ and A transpose. And the second case, when we want to know the gradients for one particular unit here, right? When we want to know how much gradients we have for A1, then we need to consider the question of how many units in the output layer does A1 contribute to, right? A1 connect to 3 units here, right? The forward pass indicated by these black arrows shows that A1 contribute to the first unit, second unit, and all the 3 units. So the gradients from these 3 units at the upper layer should all affect the gradients for dA1, right? Because we already have the forward pass constructed. Then we must use the information from all these 3 units would affect the gradients for dA1, right? So if we write down the formula here, dA1 is actually needs to use the weights W11 times the DZ1 here, right? The second unit, DZ2, DZ3, right? So if we look at the coefficients carefully, it'll be exactly W2 transposed times DZ02, okay? So those transpose operation, basically, they are reasonable, okay? They are the reasonable and the correct way to collect information about how the output is affected by the input. I see a question about, yeah, good points. Let's see. So does all nodes always have connections to, those node always need to connect to all the nodes in the next layer. So that is not, that's a good point. So in practice, we don't necessarily do that. And we will see in the next lecture, actually, there's a technique called dropouts that we actually sometimes especially for very deep network, we want to drop out some connections when we train the model, okay? Because if the model with the same structure get trained over training data again and again, it's very easy to cause overfitting issue, right? But by dropping some weights randomly, basically, when we train the model, it creates some randomness, okay? Which is good for the model so that it's generalizes much better to new data. Yeah, that's a good point. All right. So let's do a recap about the neural network, summarizing the forward and the backward processes real fast. Okay, so first of all, let's use a single data. So whenever we use a single data point, we use lowercase notations, right? We use lowercase small x. So the formula is like this, right? Forward pass, like compute z and a, right? And a used to compute z2 and a2, right? And in the backward pass, we first compute dz2, dw2, db2, right? And then we compute the dz1, right? dw1 and db1, right? So now if we want to basically vectorize over a batch of data, right? That's what our usual practice, very common practice. So we will basically do the same thing as we did for logistic regression, right? We basically needs to sum up all the gradients for each data points, okay? And kind of normalized by the number of data points in the batch. I see a question, would that be how adversarial network work? Instead of dropping weights, we would need. So I see the term adversarial. I think when we talk about, especially if we talk about generative adversarial network, GANs, I think that is not what the GANs is referring to by dropping the weights, okay? So the GANs model is more about like training two networks in the same time, while the two network they are separate. They are working on the opposite goal. Okay, one network is used to classify true from false, true from fake, like whether it's an actual image or fake image. Then the generator is trained to fool the discriminator. Okay, it's the term adversarial in GANs is used to describe this discriminator versus generator network architecture, but I don't think it's used to describe the operation to drop weights. Okay, the drop weights is described by the term dropouts. Okay, which we will definitely talk about in the next lecture. All right, going back to vectorizing over a lot of training examples. So now we basically don't use a single vector, but we stack all the units into a matrix. So the formula remains the same, but you see the input is a matrix now, and the output Z would also be a matrix. That has the same number of columns. Okay, so it also have m columns, which is the same m as in the inputs here. And the A is also the same shape as Z here. Okay, so that's the forward pass. And then in the back prop, then let's do a little bit comparison. If it's a single example, so because here we use a single unit as output for logistic regression, basically, right? And they assume that it is a sigmoid function. Then the dz2 here would be a2 minus y, and dw2 is the dz2 times a1 transpose, right? And db2. That's what we already know. And by backprop this dz2 to dz1, we would have this formula, right? And dw1 and db1. And for if we have m examples, and it's basically the same thing, right? So dz, capitalized dz, would be a2 minus y. So now y is also a capitalized y, which means it is a long vector. And a is also a long vector, okay? And that has m elements in each, okay? So dw would be dz times a1 transpose, but now we have 1 over m because we need to basically normalize the results, normalize the gradients for all the m examples, okay? And db is basically because the dz is like a very long row vector. We should sum up all the vectors, all the elements in each row, and it's not. It's more or less the same as a normal summation for dz2 because z only has 1 unit, right? It's just one output units in this network, okay? But when you have multiple units, then the row sum would be different from a normal from a summation function, okay? And for each row, we compute the sum and normalize by m, okay? So that's db2, and if we backprop this to the previous layer, this step is more or less the same as this one by replacing the lowercase z with dz, and this one also same as this one with additional 1 over m, and this one is also 1 over m but with row sum, okay? So this row summation, if we consider z1, the shape here, okay, the z1, because dz would be the same shape as z1, so we basically need to sum up all the rows for all the rows in it, okay? Not by summing up all the elements at once, but for each row, you compute the summation. Alrighty, now let's look at the next. I think at the end of the day, when we implement a network, we want it to work, and a very common and practical technique is to check the dimensions. When we are not sure about the dimensions, we basically by looking at the results of multiplying 2 matrices together to see whether the matrix dimension, the resulting matrix has the correct dimension. So for example, this is the backprop formula for m examples. Now the dz2 and a1, they basically dz2 has n2 by m dimensionality because we stack all the m examples into column vectors, right? And a1 transposed, then m it becomes here. So when we multiply these 2 things together, the m will eliminate, and the result will be n2 by n1, which is correct, right? Because it's the dimension for dw2, right? which is the correct value. And for that, for the DZ one, for example, let's do the check again. So this time we transpose W2, right? It becomes N1 times N2. And now we multiply with DZ2, which is N2 times N, and then N2 also eliminates, which results in N1 times N, right? Which I think is the correct value for DZ1, okay? So that's dimensionality check. And for the row summation in NumPy, because we will have a homework for neural network backpropagation. Then in NumPy in particular, when we want to sum the row summation, when we want to compute the row summation, we can call summation function by setting the axis to be 1, okay? And also we want to keep dimensions to be true so that the dimension is reserved, is like reserved, yeah. It's capped, it's not lost, okay? So that is just a I would say ad hoc technique, or it's just a little trick in NumPy, because when you multiply things together, you want to keep the dimensions so that it will be used in the next step. Okay, so this axis equals 1 means that the summation will eliminate the axis, the second element, the axis 1, not the axis 0. Okay, and for the row summation here, we need to use the same arguments. Okay, so now let's just redraw the picture, but this time with multiple examples. It's more or less the same, right? Forward pass, second layer forward pass, backward pass, right? And second layer for backward pass. So these will be useful, I think, when you do the homework this time. All right. So I have some example in PyTorch, backprop in PyTorch. So this example is copied from the official websites of PyTorch. Okay, so I think they have in this example, it's not just regular networks involved in here, okay, but also some convolutional layers. So we don't need to care about how convolutional layer work, but as we can see here, we can define the linear layers here, okay? So, but their dimensions match, okay? The 120 matches the 120 here, and the 84 matches 84 here. And we call it FC because it's for fully connected, okay? That's another name for usually the dense network, okay? And how the forward pass is defined is within this forward function, okay? In this forward function, we just call, use the X from the previous layer to feed into FC1 and call the value, and that'll be the resulting X will be the input for the next fully connected layer with the value, and X will be fed to the last fully connected layer. And the last X will be returned as the final result for the forward pass. Okay, so this kind of style of writing code to define models is very common in PyTorch. So it's basically defining a class with whatever name you want, and then the class should be inherited from this NN-DOM module. Okay, that is the important step, and you need to rewrite the forward function and also the constructor function here. Okay, so in the construction step, in this initialize function, we need to define the structure, define the architecture of the model, and in the forward function, we define how data flow through the forward pass. Okay, and we don't need to define the backward because the auto gradient computation in PyTorch will handle that for us. Okay, so if we visualize it, it will be kind of like this, the network. All right. So yeah, this is some additional steps like showing how the network computes the gradients. So I think it's something we have seen in the previous in the backprop example that I shown before, right? But this time a little bit different, more advanced is that we use a already predefined function, which is called mean square error loss, right? That's our something that we quite familiar with when we do linear regression, right? So we just use the predefined function to compute the loss. And when the loss is computed, right, we can basically look at the gradient function of the loss, and we can let the loss backprop, call the backprop function on top of the loss variable. Okay, so we'll give more complete example when we introduce the deep network and deep convolutional network. All right. So let me quickly check how many slides I have left. Right. All right. So we have actually shown this, right, in our example. When we initialize the second layer in our example, we let it to be all zeros, and the results is that all the outputs would be zero, right? And when we do the backprop, the DAs to the previous layer is also zero, because whenever how we transpose W, they are all zeros, which will not give a different output, right, other than zero. So it actually tells a problem about initialization weight parameters. We don't want zeros basically. When the parameters are zero, then all the outputs are identical. So and the gradients are all identical, all zeros. So which means we don't actually train the network. The network, it doesn't learn anything because all the elements are the same. And all the updates to all the rows, to all the elements, to all the parameters are the same. Okay, so all the hidden units compute the same function. Then it doesn't matter. It doesn't make sense to set that many hidden layers. So we want randomness in the parameters. And a common way is that we set the parameters to some random numbers drawn from a normalized distribution, and to make it into some really small values. Okay, so in PyTorch, in NumPy, for example, we can use a 4x3 random, a 4x3 NumPy array randomly drawn from some normal distribution, and then times some constants. Okay, so this is a pretty manual way of initialization. And actually in PyTorch and other frameworks, we have pretty standard way of initializing all the parameters. Okay, and in the next lecture, we're going to show why it matters to initialize parameters in certain ways. Okay, because when a model, so simply speaking, when a model is big, it is hard to train. It is hard to let all the parameters to get updated through gradient descents. Okay, gradient descent becomes not that easy task. Okay, all right, that's pretty much for the network here. And here are some tips that are useful in the homework. So that's it for the back propagation. And I know it's quite a lot of content, and I hope you can use the example that I put in the slides, and also use the homework as a way to practice. Okay. Any questions?
Yeah, when do you plan on releasing the next homework?
So I will double check to see if they're ready. If so, I will probably release it tonight.
Okay.
Yeah. All right.
I have a quick question, and when would that be due if it's going to be released tonight?
Next Friday, most
Okay.
likely. Yeah.
Thank you.
Yeah.
Professor,
Yeah.
about the second tip, this element-wise operator versus vector. I
Mhm.
know you said something in between the lecture. Can you please repeat it briefly?
Yes.
Thank you.
Yeah. So actually, it's something that's I can talk about right now. Let me find the equation. Too much slides ago. So let me find the page for propagation right here. Yeah. So the first time it appears is here, right? Right here. So the gradients for dz would be gradients for dA with a element-wise multiplication with the partial derivatives of A1 with respect to Z1. Okay, so that is because you see the mapping relationship between A and Z is 1-to-1 match. Okay, so the computation of A1 is only relied on Z1, and A2 is only relied on Z2. So it's just the activation functions that's taking effect between Z1 and A1. So Z2 doesn't contribute to A1. So we don't need to consider this cross elements relationship. We just need to compute, we just need to know the gradients. We just need to know the partial derivatives of A1 with respect to Z1 if we want to compute the gradients of Z1. Okay, and we use a element-wise multiplication in this case. So, for example, there's a partial derivative of A1 with subscript 1 with respect to the Z1 and subscript 1. So this is a partial derivative. That is particularly for this unit. And for the second unit, there will be a different value, which is partial derivative of A1 in a superscript, but with 2 in a subscript with respect to Z1, but 2 in the subscript. And this quantity is particularly used in this unit. Okay, and this one is a vector. This partial derivative is a vector. That is the same shape as A1. Okay, as dA. Okay, the dA is also a vector, and the dz is also a vector. Okay, so all these three vectors have the same dimensions. Is that clear enough?
Yeah, Professor. Thank you.
Okay, yeah, I think through the practice of the homework, it'll be the whole picture would be much more clear. Quiz today, I don't think there will be quiz today. Yeah, so I released all the quiz questions about backprop in the previous after the previous lecture. Yeah. Okay. All right. So next Thursday we're gonna enter the next lecture, which is about deep neural networks. We'll see some practical tricks of training much deeper networks. Yeah. All right. Thank you. See you guys.